Right now, without you feeling a single thing, the ground beneath your feet is pulling on you slightly less than it pulled on your grandparents. Not because Earth is shrinking, not because physics has changed, because the mass of this planet is moving. Gravity is not a fixed, uniform blanket draped over our world. It is a living map, one that has begun to redraw itself in ways that are now disturbing the orbits of satellites, bending the truth of our GPS systems, and quietly threatening technologies billions of people depend on every day. This is not science fiction. This is already happening. Most of us were taught gravity as a simple equation, one number, one force, pulling everything equally downward. That picture is wrong. Earth's gravitational field is a geoid, an invisible, lumpy surface traced by variations in mass. Where more mass concentrates below you, gravity strengthens. Where mass is removed or shifted, the field weakens. Over Hudson Bay and Canada, gravity has been measurably weaker for thousands of years because the last ice age pressed so much weight into the crust, the mantle below was displaced and has not fully returned. The Earth is still recovering from an event that ended 10,000 years ago, and the field reflects every scar. Minus 45 milligal, Hudson Bay gravitational anomaly below global average, one of Earth's largest persistent gravity deficits, a scar left by the Laurentide ice sheet. In 1672, French astronomer Jean Richet carried a precise pendulum clock from Paris to Cayenne near the equator. The clock lost 2 minutes and 28 seconds per day. He had no explanation. Newton did. The pendulum swung slower because gravity was weaker at the equator, because Earth bulges outward there, placing the pendulum farther from the planet's massive center. Nearly 300 years later, the very first successful American satellite, Vanguard 1, gave humanity its first empirical proof that Earth is not a perfect oblate spheroid. Its orbit wobbled in ways that could only be explained by mass irregularities no map had ever shown. The age of gravitational mapping had begun, and what scientists found would take decades to fully terrify them. In 2002, NASA and the German Aerospace Center launched GRACE, the Gravity Recovery and Climate Experiment. 2 satellites flying in formation, separated by exactly 220 kilometers. Between them, a microwave ranging system so sensitive it could detect a change in distance smaller than a single strand of human hair from space. When the lead satellite passed over a region of higher mass, gravity pulled it forward slightly. The gap between the 2 satellites changed. That change was recorded. Over 15 years, GRACE built the most precise gravity maps in human history. What GRACE revealed was unambiguous and alarming. Greenland was losing an average of 280 billion tons of ice per year. Antarctica, another 150 billion. The water cycle was redistributing mass at a scale no model had predicted. And as ice left the poles and entered the oceans, the gravitational field of the planet, its very fingerprint, began to change. 280 gigatons per year, average annual Greenland ice mass loss measured by GRACE satellites, enough water to fill Lake Erie every year, permanently removed from the poles. Every satellite in orbit is in a constant negotiation with Earth's gravity. Its altitude, its speed, its ground track, all of it is calibrated against a gravity model that engineers assume is stable. But the gravity model isn't stable anymore. As mass leaves Greenland and Antarctica, the gravitational pull those regions exert on nearby satellites drifts. Ground tracks shift by meters. GPS signals, which rely on knowing a satellite's precise position within centimeters, begin to accumulate errors. The Earth's geoid is the reference surface against which all satellite-based height measurements are made. When it shifts, every elevation reading on the planet becomes slightly wrong. Flood maps, aviation guidance, financial systems that timestamp trades with GPS clock, infrastructure monitoring, all of it relies on a gravitational baseline that is now in motion.
Scientists must now continuously update the Earth gravitational model, the reference document used by every GPS chipset on the planet, something that was once done every decade, but now demands near annual revision. As ice melts, the bedrock beneath it rises. This is called glacial isostatic adjustment, the crust rebounding from weight it has carried for millennia. Parts of Greenland are rising by over 2 centimeters per year. Bedrock that was depressed under kilometers of ice is now moving faster than at any point in recorded geological history. Mass redistribution does not just change the field, it changes the planet's moment of inertia, the distribution of mass around its rotation axis. The poles themselves migrate. Since 2000, Earth's rotational pole has shifted by approximately 4 meters eastward, driven almost entirely by the loss of ice from Greenland and West Antarctica. The axis on which our entire planet spins has moved because we melted ice. 2% of the Greenland ice sheet volume lost since 1992, a sign of rapid change visible in geodetic maps. Earth's day is also lengthening. As meltwater flows from poles to equatorial oceans, it moves mass outward, like a spinning figure skater extending their arms. The rotation slows by fractions of milliseconds per century, enough that atomic clocks, GPS systems, and financial exchange servers must account for it. Over the South Atlantic sits a region known as the South Atlantic Anomaly, a vast zone where Earth's magnetic field is weakest and where the Van Allen radiation belts dip closest to the planet's surface. But beneath the magnetic mystery lies a gravitational one. Deep below this region, the mantle is dense, cold, and ancient, a relic slab of oceanic crust that subducted hundreds of millions of years ago and never fully assimilated. Every satellite that passes through the South Atlantic anomaly is bombarded with elevated radiation. Electronics glitch, memory errors spike. The Hubble Space Telescope routinely suspends observations during passes through this zone, and the anomaly is growing, expanding westward approximately 0.3 degrees per year. Scientists are unsure whether the ancient slab below it is moving, whether the core beneath it is shifting, or whether something deeper still is in motion. It is a reminder that the forces shaping Earth's gravity are not only on the surface, they reach all the way to the planet's heart. There is something profound and unsettling about the fact that the very gravity of this world is now a variable. It was always assumed to be the one thing beneath change, the constant, the foundation of every calculation, every structure, every orbit we have ever launched into the sky, and it is not. In the Maldives, sea level is rising, but near Greenland, paradoxically, the sea is actually falling because as the ice sheet loses mass, its gravitational attraction on the surrounding ocean weakens and water pulls away. The ocean is responding to the same gravity that is changing beneath the satellites above. We are living through the first era in human history when the shape of gravitational reality around our planet is being altered by human activity, and the machines we built to navigate our world are now sailing with a map that must be continuously redrawn. Gravity is the oldest force in the universe. It built planets from dust. It holds oceans against spinning rock. It keeps every satellite, every signal, every calculation aligned with the world it serves. But Earth's gravity is a portrait of Earth's mass, and Earth's mass is no longer where it used to be. Grace FO continues to watch. Scientists continue to update the models. Engineers continue to correct the orbits. The satellites adjust. The algorithms adapt. But the deeper question, how far will this go and how fast, remains, like the anomaly over the South Atlantic, unanswered. We live on a dynamic world. We always have. The difference now is that we are the force that is changing it, and our machines are watching.